So if you had a go on the weekend doing it by first principles, you'll appreciate what a pain in the neck that is, doing it that way. But the wonderful thing about maths, all types of maths, is we look for patterns, and there is definitely a pattern when it comes to first principles. So in reality, we only ever use first principles in one of two situations. One, if it's a new function that we don't know how to differentiate, then we can use it to come up with a formula for that. Or two, of course, is in an exam if they say differentiate by first principles. Then, of course, we've got no choice. So let's go through step by step each type of function, starting with the simplest function, which would just be a constant number. Now, if we remember what a derivative measures, that being the slope of the tangent at a particular point, if I was to draw the line y equals a constant, what would the slope of that graph be? Yeah, it's going to be a horizontal line. So what we should find is it doesn't matter what the constant is, the derivative will always be 0. But we can prove that using first principles. So function x would be a constant. Function x plus h would also be a constant. If we put it into our formula, then on the top we get constant minus constant, which sure enough is 0. 0 divided by h, well, it doesn't matter what h is, we'll get 0, and now there's nowhere to substitute in for h, so yes, it's always 0. So we know that if we have to differentiate a constant number, we get 0. Okay. The next type of function would be a straight line. So some constant times x. And again, because it is a straight line, we know what the answer should be. The answer should be k. So we know the slope of the line is the coefficient of x. Well, let's see what happens. Function x is kx. Function x plus h would be k times all of x plus h. Put it into our first principles formula. So on the top we get kx plus kh minus kx. The kx's now cancel. And I have kh on h. Oh, well, now that's my factorised. Well, you can't factorise it, but we can cancel. And again, we get k. There's no h there, so it's always going to be k. Thus proving that the derivative of any straight line is simply its slope. So if we get a question, differentiate 5x, I don't have to go through this. I know the answer is 5, because that's the slope of the line. What about polynomials in general? So x to some power. Now, in order to do this, I need to remind you of something we saw back when we were doing algebra. Remember, we have a formula for difference of two squares, a squared minus b squared, and then we expanded that. We said, oh, look, we've now got one for 2 cubes. And then we said, hey, we could actually generalise it, because a to the 4 minus b to the 4, there's a pattern there. And so if we get a to the n minus b to the n, we know it'll always factorise to be a minus b. And then the powers of a go down by 1, the powers of b go up by 1. Okay. So I'm going to use that in proving this next one, x to the power of n. Function x is x to the power of n. Function x plus h will be x plus h to the power of n. So if I put that into my first principle formula, there it is, a to the n minus b to the n. It's just that a is x plus h and b is x. So I know that will factorise to be a minus b in the first parenthesis, so x plus h minus x. The powers of a, x plus h, are going down by 1. So n minus 1, then n minus 2, then, and so on and so on. And the powers of x are going up by 1. So it starts with x to the power of 0, then x to the power of 1. And we keep going until that last one there, x to the power of n minus 1. But the interesting bit's the first parentheses. You see we've got x plus h minus x, which is just h. And that will cancel with the h on the bottom. And that will leave us with a whole heap of these, x plus h to the power of n minus 1, then x plus h to the n minus 2x, and so on. But we're interested when h approaches 0. So if h approaches 0, this expression is going to become x to the power of n minus 1, x to the power of n minus 2 times x, which is x to the power of n minus 1. Then the next one, I mean, it's not written there, but the next one would be x to the power of n minus 3 times x squared, which is x to the power of n minus 1. And every single one of them, and obviously the very last one is x to the power of n minus 1, every single one of them is x to the power of n minus 1. The question is, how many of them do we have? Now, we can answer that question by going back to here. When it was a squared minus b squared, so when the power was 2, we had 2 terms in the second parenthesis. When the power was 3, we had 3 terms in the second parenthesis. When the power of 4, we had 4. So logically, if it's power of n, how many terms do I have in the second parenthesis? That's right, n. And we said each one of them is x to the power of n minus 1. So I must have n lots of x to the n minus 1. And there's now our shortcut, our formula for differentiating x to the power of something. All I've got to do is get the original power, put it to the front, and then subtract 1 from the power. So differentiate x cubed, it'll become 3x squared. X to the power of 5 will become 5x to the power of 4, and so on. So I don't need to use first principles. I can just use that pattern every single time. So now we should be capable of doing any polynomial whatsoever. Well, what about negative indices? So when it was a positive power, because we said polynomials, I could just bring that power down to the front. Will the same thing apply? We'll have a look at 1 on x, see what happens. So function x is 1 on x. Function x plus h is 1 on x plus h. Putting it into first principles formula. 1 on x plus h minus 1 on x all over h. A little bit ugly, but it's just an algebraic fraction. So my common denominator, well, h is on the bottom. I'll also have x on the bottom and x plus h on the bottom. The first fraction, the numerator becomes x. The second one is minus all of x plus h. The top just becomes minus h. The minus h will cancel with the h in the bottom. And I now have minus 1 on x times x plus h. We're interested in when h approaches 0. So that will become minus 1 on x squared. So could I have used the other formula? Well, let's have a look. Had I gone function x is and put it into negative indices, our rule said get the original power, put it to the front, subtract 1 from the power. So if I've got x to the negative 1, I move that to the front, negative 1, subtract from the power, negative 2. Well, minus x to the power of negative 2 is indeed minus 1 on x squared. So our formula that we created there for polynomials works for negative indices as well. We don't need a new formula. Well, that leaves us with one more type of question. So great, we've covered positive integers, negative integers, but our powers can also be fractions. Let's have a look. We'll do it with the square root of x. Let's see what happens. So function x will be the square root of x. Function x plus h, the square root of x plus h. Put it in the first principles formula. There it is. Square root of x plus h minus the square root of x all over h. I'm going to do something which is familiar, but the opposite. Normally when we see a fraction with surds, we rationalise the denominator. I'm going to rationalise the numerator. But it's the same idea. I'll just multiply by square root of x plus h plus square root of x. So on the top, I get x plus h minus x, but on the bottom we now have h times the square root of x plus h plus square root of x. But look what happens. On the top, I've got x plus h minus x. That's just h. And the h will cancel with the h. And now I've got something I can substitute into. Because if I substitute into that, the square root of x plus h just becomes the square root of x. And so I have 1 on root x plus root x, which is 1 on 2 root x. Did my formula work? Well, if I'd done it by changing it to indices, I would have said function x is x to the power of a half. Get the original power, put it to the front, subtract 1 from the power. I would get a half x to the negative a half. Well, negative means I'm on the bottom of the fraction. That is 1 on 2 root x. So yes, the formula works for fractional powers as well. So we can use that one idea of get the old power, bring it to the front, subtract 1 from the power, it will cover all of x to the power of anything. So life now becomes very much simpler and quicker. I don't have to use first principles. They give me a question like y equals 7, we can just go, ha! And it's important you do that too. You go, ha! The derivative? That's simple. If I've got a constant, the derivative will be 0. Now be careful in your setting out. They are different things. So I see some setting out where people go, y equals 7 equals 0. And they don't put the y dx in there. Well, mathematically what you're writing down is wrong. You know, it's because 7 doesn't equal 0. It's the function equals 7, the derivative equals 0. What notation to use? If they start with y, I tend to go with the y dx. Or you could do the y dash, I suppose. Whereas if they started with function x equals 7, then I'd go f dash x. I kind of match the notation in the question. Y is 37x. Ha! Trying to make it look hard by putting 37 there. That's just 37 when we differentiate it. Who said this calculus thing was going to be hard? Oh, power of 10, big number. Y equals x to the power of 10. The derivative will become... original power comes to the front. Subtract 10x to the power of 9. There's 3 things there. We didn't talk about that. Beautiful thing about the calculus is we just do each bit by bit. So differentiate 3. Oh no! 3x squared. I know how to differentiate x squared. How would I differentiate 3x squared? Yeah, I'll just multiply by 3. So when I bring that power to the front, I'll multiply by whatever number's there. So the 3x squared becomes 6x. The 6x becomes 6. The 2 becomes 0. I don't write the plus 0 down. But there's my derivative, 6x plus 6. 2x plus 1 all squared. Ah. So tempting just to bring the old power down and subtract 1. Can't do that. We will see another rule later on which shows us how to do this without expanding. But for this stage, pretend we know nothing about that. If you do already know that rule, just pretend. Don't know. Ooh. So we're going to have to expand it out at this stage. So that's 4x squared plus 4x plus 1. Differentiate 8x plus 4. 3x plus 1 on x squared. Going to have to change the 1 on x squared to index form first. Now here comes the first mistake people make with this sort of question. Because you've done something, change the 1 on x squared to the x to the negative 2, people feel like, oh, I've done something, I must have answered the question. But you haven't yet, because the question is find the derivative. So differentiate it, 3 minus 2x to the negative 3. That's good enough for an answer, but I tend to write it in the way they wrote it. So if they didn't use negative indices, I'm just going to convert it. So I guess the first line there, dy dx, 3 minus 2x minus 3 would be a mere mortal's way of answering the question. But us super mathematicians would go 3 minus 2 on x cubed. I think if you have to substitute numbers in, because it all depends what you're going to go and do with it. If I had to substitute a number in, I think the second line's easier to substitute into than the first line there. X squared root x. Oh, whoa, now you're really trying to confuse me. That would be x to the power of? Right. Remember the quick way of thinking about it? X to the power of 2, x to the power of a half. So it's 2 and a half, which is 5 on 2. Old power goes to the front, subtract 1, 5 on 2, x to the 3 on 2, mere mortal answer. Super mathematician answer, 5 on 2, x root x. And in between mere mortal and super mathematician, there's a middle stage in there where some people might write square root of x cubed. What would we call those people? What's in between mere mortal and super mathematician? What is it? A mediocre. Okay. All right. Be very careful that you read the question. If function x equals x cubed minus 3, find f dash 2. Very easy to misread this question and just think you're finding function 2. No. This means substitute 2 into the derivative. And they've used function notation So when I differentiate, I'll use function notation. So f dash x is 3x squared. F dash 2, then substitute 2 into the derivative, and there it is, 12. Of course, the very question that we wanted to solve when we started all this, how do we find the equation of a tangent to a curve? So here is a question like that. The curve is a cubic. Y equals 5x cubed minus 6x squared plus 2. Imagine if I was going to do that by first principles. That would just, huge yuck. But we don't have to now. And we're going to be at the point 1, 1. We're going to find the equation of the tangent. So in our head, tangent, that's a straight line. Find the equation of line. I need two things, a point and a slope. I've got a point, 1, 1. Yes. Slope. Oh, no. How do I find the slope? I got calculus now. I can find that. Y equals 5x cubed minus 6x squared plus 2. Differentiate it. Remember, that's not the slope of the tangent. That's the formula that allows us to find the slope of the tangent. We want when x is 1, so substitute 1 into the derivative. Our slope is 3. We have a point, we have a slope, and we have this beautiful formula, the point-slope formula. Y minus y1 is m outside of x minus x1. Tidying it all up, there it is. I put it in general form. So 3x minus y minus 2 is equal to 0. Find the points on the curve y equals x cubed minus 12x where the tangents are horizontal. So we want to know if we were to draw tangents in, they'd end up being horizontal lines. So what is that actually asking me? There's the curve. There's my derivative. Tangents are horizontal. What's one fact you can tell me about a horizontal line? Gradient is equal to 0. We now have a formula that will find 0. And that's what it's basically asking. When is the derivative equal to 0? When will the slope of the tangent end up being 0? So we know they're going to be horizontal when the derivative is equal to 0. When you're doing your working out, explain what you're doing. Don't just go, 3x squared minus 12 equals 0. Like you've pulled it out of thin air. Explain what you're doing. Well, I know tangents are horizontal when the derivative equals 0. So that's why I'm solving this equation 3x squared minus 12 equals 0, which has plus or minus 2. There are 2 points. Classic mistake that's now made. To obtain the y value, people sub into the derivative and amazingly come up with the answer 0 because it's a stationary point. But no, it's the y value you substitute in to get the y value, strangely enough. And it's a nice symmetric curve it looks like here, because look at that. One's turned out to be 16, one's turned out to be minus 16. Makes sense. Look at the curve. What type of function? Odd. Who said even? All the powers are odd, so it's an odd function. Okay. Bit of terminology. Tangents we've been dealing with ages. We know what a tangent is. There's this other important line we deal with. It's called a normal. And all a normal is a line perpendicular to the tangent at that point where it meets the curve. So here's random curve. That is a tangent, of course. The normal is the line at right angles at the point of contact. So if they say, find the equation of the normal, how do I find the equation of a normal? I need a point, I need a slope. I've got a point, yes. Slope, how do I find the slope of a normal? Don't know how to find the slope of a normal, but I can find the slope of the tangent. And then once I know that slope, it'll be the negative inverse because it's perpendicular to it. So I do it just like the tangent. There's my function, my derivative. We're at the point when x equals 3. That's 21, but that would be the slope of the tangent. So therefore the slope I'm interested in is minus 1 on 21. That would be, and then everything's the same. Put it into the point slope, 29 times 21. That's huge, 609. It's not as big as I thought it was. Still big though. And put it in general form, there it is. X plus 21 and y minus 612 is equal to 0. All right, let's have some fun. Thank you, Mr. Newton. Or was it Leibniz?